This video covers simple harmonic motion part 1. Now you don't need to write all of this down, but we do need to talk about what oscillatory motion is. So oscillatory motion is repetitive back and forth motion about an equilibrium position. It is periodic. Swinging motion and vibrations are forms of oscillatory motion. So a swinging motion would be something like a pendulum, and vibrations would be something like a mass on a spring. And this is known as a spring mass system. And we'll see examples of those in just a bit. Objects that undergo oscillatory motion are called oscillators. Simple harmonic motion is a type of periodic motion. So we do need to talk about period and frequency. Period, represented by a capital T, has units of seconds, and this is the time it takes to complete one full cycle of oscillation. Frequency is 1 over period. This is the amount of oscillations per second. This has units of hertz, or 1 over seconds. Another important piece is the amplitude, represented by a capital A. It's an object's maximum displacement from its equilibrium position. In a graph, it is the distance from 0 to a crest, which is the top part of a graph here, or a trough down here. You can see that this mass spring system shows the graph that we see here. So this equilibrium position is right in the center. This amplitude is the distance away from your equilibrium position, so you can see a physical meaning of that. And you can see as it reaches its maximum, it returns back to its equilibrium, past its equilibrium point, and then on to its other maximum point. So you see that happening in between. Now again, if there's no friction, would go on forever. If you look at this graph, this is a position versus time graph. So our function xt is equal to a cosine 2 pi over t times t is our position function with respect to time. Now, if you look at the inside of this cosine function, capital T is the period of this graph. T is going to be the specific times that you want to look at. A is your amplitude, and again, x is your position. Now, if you look at the situation of t is equal to 0, then what happens is that the inside of this cosine all becomes 0. Well, the cosine of 0 is just 1. So at time is equal to 0, my position is equal to my amplitude. So you can prove that this particular function, or this particular graph, actually shows a cosine function. Let's focus on this first graph to begin with. Here we can see at time is equal to 0, my position is equal to the amplitude. So we can use that first equation that we saw. Our position function with respect to time is equal to a cosine 2 pi over period times time. Now, what I want you to imagine is a mass spring system. So right now, this mass has been pulled away from its equilibrium position. So when time is equal to 0, we're starting off at our amplitude. When I let it go, it's going to start oscillating back and forth between its maximum amplitudes. So this next part, there's 2 different ways that you can think about it. Because this is a position versus time graph, we know that the derivative of position with respect to time is equal to velocity. So I can take the derivative at this point, and it should tell me my velocity. So if we look at the slope at that point, we get a flat line, so that means my velocity is 0 there. So here, you see my velocity time graph also reflects that. Let's say if we were to take the derivative at this point, again, a derivative is just the slope of a tangent line. So if we look at the slope of a line at that point, we do have a negative velocity, but it's actually pretty high. So if we look over here at our velocity time graph, we should see it also reflect that. Again, this low point here, we have a velocity of 0, so we should see that as well. And then you can follow through the entire graph and you see that these different points will match up. So the derivative of the position versus time graph is velocity versus time. Now, the other way you can think about it is looking at this mass and spring. We know that if I were to let this object go, it's going to start speeding up as it moves through this position. The maximum velocity will be here at its equilibrium, but it's not going to stop there. It's going to go right past it, and then as soon as it goes past it, it starts to slow down. It slows down until it stops at its amplitude. When it reaches that point, it turns around and starts to speed up, go past its equilibrium again, reaching another maximum velocity, but now it's pointing to the right. So here we have a positive velocity at this point. Here, because it was moving to the left, we had a negative velocity. So either way, you should be able to figure out what type of graph I'm going to get just from looking at the situation or the position versus time graph. Now let's look at this equation one more time. Here we have the position time function is amplitude times the cosine of 2 pi over period times t. So from what we just saw, I have t at the bottom of this fraction. So really, this is 1 over t times 2 pi times t. That means I can rewrite this as a cosine 2 pi frequency, because 1 over period is frequency, times time. So this is another way to write this equation. Another thing is if you go back to our rotation information, remember that velocity around a circle is equal to 2 pi r, which is the circumference of a circle, divided by period, the time it takes to move around that circle. Well, we also know that velocity is equal to r times angular speed. Well, if these two equations are equivalent, then that means that 2 pi over t is equal to angular speed. And in this case, we're going to refer to it as angular frequency. So angular frequency is 2 pi over t, and another way to write that is 2 pi frequency. So this is a very important relationship. That means that this position time function can also be written as omega t. And again, this is a very common way to see this equation. Here's a summary of what we just saw. Even though we're referring to omega as angular frequency now, it still has units of radians per second. So if you look at this equation, and if I write radians per second here, and I multiply it by time, which is also in seconds, my units cancel out and I'm left with radians inside of my cosine. What that means is that your calculator needs to change modes. So you need to make sure that when you are doing simple harmonic motion problems, that whatever you put inside of your cosine is in radians. So make sure you make that change. Calculator. So again, velocity is the first derivative of the position with respect to time. So I need to get the derivative of this cosine omega t function. Now when you take the derivative of a cosine, it is simply, a is a constant, negative sine. You leave everything that's already there, and then you multiply it by the derivative of the inside. Now, since we're taking it with respect to time, omega here is a constant. So the derivative of omega t is just omega. So this function for velocity is equal to negative a omega sine omega t. And again, you can see how this, if we plot this graph, or this function, we get this graph over here. So again, we can double check it. Let's say that I want to look at my velocity when my time is equal to that of a fourth of a period. Okay, so we're evaluating it at time is equal to a fourth of the period. A and omega stay the same. And I can replace t, time, with period over 4. Now we just said that omega can be rewritten as 2 pi over t. So we can see that the periods will cancel out and the fraction will reduce to pi over 2. So the sine of pi over 2 is just 1. So that means at my time is equal to period over 4, my velocity will be equal to negative a omega. So my velocity is negative at this point. And again, because velocity is a vector, if it's negative, that means it's moving to the left. Now we can do the same process for the time three-fourths the period. So we have negative a omega sine omega t. We can replace t with the new time that we're looking at. So we're evaluating this equation. Remember that omega can be replaced with 2 pi over t. The t's will cancel out. The 2's will reduce. And you're left with 3 pi over 2. And the sine of 3 pi over 2 is a negative 1. So these negatives will cancel out. And your velocity is now a positive a omega. So that means that anytime we get a omega, we are looking at our maximum speed, not velocity, speed. So here, we can rewrite this equation, this velocity equation, as negative maximum speed times sine omega t. And you'll see a summary of this in just a moment. Again, here I am showing V max, but this is referring to maximum speed, not velocity. It's just this is the way you're going to see it on equation sheets, so I just want to make that distinction. We can also solve for our acceleration function, which remember is the derivative of the velocity function with respect to time, or the second derivative of the position function. So again, our function for velocity was negative omega a times the sine of omega t. And if we take the first derivative of that, then we get negative omega squared times a times the cosine of omega t. Now, if we needed a phase constant, we can just simply add a phase constant here and add a phase constant here. Again, because they're constants, it doesn't affect the derivative. So if our acceleration function is negative omega squared times a cosine of omega t, well, you can recognize the second part of the equation and simply our position function. So if we needed to, we could replace that section with just x. So what this tells us is that acceleration is proportional to the negative of the displacement. Meaning where position is maximum, acceleration is minimum. When position or displacement is minimum, when you have negative xa, then you have a maximum acceleration. If the net force acting on a particle is a linear restoring force, the motion will be a simple harmonic motion around the equilibrium position. And we'll see a couple of examples of what that means.